Welcome to another deep dive.
Great to be here.
Today we're taking a deep plunge into the, well, often misunderstood world of Bitcoin. It's fascinating, isn't it?
Absolutely.
You've probably heard the headlines, seeing its price soar and dip, but have you ever wondered how it actually works? Beyond just being like digital money.
Yeah, and our guide for this particular dive is a real classic. Mastering Bitcoin, Programming the Open Blockchain, the second edition by Andreas M. Antonopoulos.
A foundational text.
Definitely. And our mission today is really to pull out those crucial nuggets of knowledge, those key insights,
Right.
to help you truly grasp the foundational concepts and maybe some surprising facts that make Bitcoin tick.
And what's so interesting right from the start is that Bitcoin wasn't immediately seen as this revolutionary thing.
Right.
Not even by early people like Antonopoulos.
No, he admits it. His first reaction was kind of 50 nerd money.
Yeah.
But he pretty quickly realized, wait a minute, this is much more than just digital cash.
What was it then?
He called it a decentralized trust network.
Okay, decentralized trust network. Let's unpack that phrase because it sounds really important.
It is.
What truly underpins Bitcoin beyond just the currency aspect? And why is that such a game changer?
Well, at its absolute core, Bitcoin really represents the culmination of, decades of research in cryptography and distributed systems.
Right.
It cleverly brings together four key innovations. First, you've got this decentralized peer-to-peer network. That's the Bitcoin protocol itself.
Okay.
Second, there's a public append-only transaction ledger. That's what we call the blockchain.
Famous blockchain.
The very same. Third, a really precise set of rules for how transactions are validated independently and how new currency gets issued. And finally, there's a distributed computation system powered by something called a proof-of-work algorithm.
Proof of work, we'll definitely need to get into that later.
Oh, yeah. But the real genius, the true insight here, is how these, seemingly separate components work together. They synergize to create a system that can establish truth and trust without needing any central authority.
Trust without a central authority. That's a powerful claim.
It is.
Because we've seen attempts at digital money before, and they mostly failed, right? Why was this specific architecture so critically needed?
Yeah, those previous digital currencies, they worked, sort of, but they were inherently centralized.
Which meant?
Well, it made them vulnerable, really vulnerable, to attacks from governments, hackers, or just, the whims of whatever company was running it.
So a single point of failure.
Exactly. They consistently failed. Satoshi Nakamoto's key innovation, which was laid out in that 2008 white paper, Bitcoin, a peer-to-peer electronic cash system.
A foundational paper.
The key was solving the double spend problem.
Yeah.
How do you stop someone from spending the same digital money twice?
Without a bank in the middle checking everything.
Oh, yeah, precisely. Instead of a central clearinghouse, Bitcoin uses this global election. It's based on computational power, and it happens roughly every 10 minutes.
An election.
In a way, yeah. It allows the whole network to collectively agree on the legitimate state of all transactions, on what's true.
And this idea, decentralization, it feels like more than just a tech buzzword. It almost sounds like, something you'd see in nature.
It absolutely is. Nature gives us a beautiful analogy, actually. Think about leafcutter ants.
Okay.
They form these incredibly complex societies, right? Huge colonies, farming fungus.
Yeah, amazing stuff.
But each individual ant, it operates on very simple rules. There's no queen ant dictating every single move.
The central command.
Exactly. Their sophisticated collective behavior, it just emerges organically from the interaction of millions of individuals in this, decentralized social network.
Yeah.
And that demonstrates how decentralized systems can be incredibly resilient, adaptable, and produce just remarkable complexity without any top-down hierarchy. That resilience, that's fundamental to Bitcoin.
Okay, that makes sense. All right, let's get down to brass tacks then.
Yeah.
How does the money actually flow? How do transactions work in this system?
A Bitcoin transaction, in simple terms, it's just a message broadcast to the whole network.
What does it say?
It basically says, the owner of this specific piece of Bitcoin value has authorized me to transfer it to someone else. Think of it like double entry bookkeeping, but with a twist.
A twist.
Yeah, you have inputs. These are essentially debits, but they come from specific outputs of previous transactions.
Okay, so linked back.
Always linked back.
Yeah.
And then you have outputs. These are the credits going to new Bitcoin addresses. Now, The crucial part for the system's health
Yeah.
is that the total value of the outputs is always slightly less than the total value of the inputs.
Slightly less. Where does the difference go?
That small difference, that's an implied transaction fee. It goes to the miner who includes your transaction in a block. It's their incentive.
Got it. So you mentioned inputs come from previous outputs. This sounds very different from just having a bank account balance. It's more like you're spending specific chunks of money you received before.
Exactly. That's the core insight. Bitcoin transactions are about spending specific, previously unspent outputs. We call them UTXOs, unspent transaction output.
UTXOs, okay.
It's not about subtracting from some abstract account balance like in your bank.
Why is it designed that way? What's the advantage?
Well, this radical departure ensures every single unit of value, every Satoshi, has a traceable origin and a completely transparent history.
Traceable history.
Yeah, it creates this immutable, auditable chain of ownership that's incredibly difficult to forge because you're literally proving you control a specific piece of Bitcoin, that UTXO, before you can spend it.
So it's like every digital coin has its own history attached.
Kind of like that, yeah. Imagine if every dollar bill had a unique serial number and a public record of every single time it changed hands. That's the kind of transparency and verifiability we're talking about.
And that prevents the double spending.
That's fundamental to preventing double spending without needing that central authority, yes.
Okay, that makes perfect sense now. So let's take a practical example. Alice buys coffee from Bob. How does this UTXO system actually play out?
Right. So Alice wants to pay Bob, say, 0.015 BTC. Her wallet software automatically looks at the UTXOs she controls.
The unspent outputs she owns.
Exactly. Let's say she has one UTXO worth 0.10 BTC. Her wallet has to consume that entire 0.1 Brio BTC UTXO.
Even though she only needs to pay 0.015.
Yes. It consumes the whole input. Then it creates two new outputs in that transaction. One output sends 0.015 BTC to Bob's address.
Okay.
The other output sends the change back to Alice. So 0.10 minus 0.015 minus a small transaction fee. Maybe she gets back 0.0845 BTC.
So it sends the change back to her.
To a brand new address in her own wallet, typically. It's conceptually similar to, using a $20 bill for a $5 coffee.
Right.
You hand over the $20, it's consumed, and you get $15 back as new change. The original $20 is gone, replaced by the coffee and the $15.
Got it. And those transaction fees, that little difference, how are they determined? Are they really important?
They are absolutely crucial. And interestingly, fees are based on the transaction's data size, usually measured in kilobytes or virtual bytes now.
Not on the amount of money being sent.
No, not directly. Sending 1 BTC costs the same in fees as sending 1 million BTC if the transactions have the same data size. The fee serves as that economic incentive for miners. The network is like a competitive market for block space.
So higher fees get you faster confirmation.
Generally, yes. A higher fee makes your transaction more attractive to miners, so it's more likely to be included in the very next block. Transactions with 0 or very low fees might sit in the queue, the mempool, for a long time, or maybe never get confirmed at all.
And you mentioned miners create new Bitcoin. Is that a specific type of transaction?
Yes, that's the Coinbase transaction. It's unique. It's always the very first transaction in every new block.
And what's special about it?
It has no inputs. Its sole purpose is to create brand new Bitcoin out of thin air, essentially. And that new Bitcoin, plus all the transaction fees from the block, is paid to the miner who successfully solved that block. That's their reward.
Okay, so this whole system hinges on ownership and transferring value securely, and that relies heavily on cryptography, right?
Let's talk about the keys.
Absolutely. Bitcoin ownership isn't like owning a physical coin. It's established through digital keys. Specifically, a pair of keys.
A pair.
A private key, which you keep absolutely secret, and a public key, which you can share.
And my wallet holds these.
Your wallet software manages these keys for you. It's a really common misconception that the wallet contains the Bitcoin itself.
Right, you mentioned that.
The coins are just records of those unspent outputs, the UTXOs, on the public blockchain ledger.
So how do I control them?
You control them by using your private key to create a digital signature on a transaction. That signature proves you own the inputs you're trying to spend.
And the public key.
The public key is mathematically derived from your private key. And then, your Bitcoin address, the thing you share to receive funds, is derived from your public key. Derived. So you can get the address from the public key and the public key from the private key.
Yes. But, crucially, it's through one-way mathematical functions, like hashing. You can go forward easily, but you can't reverse the process. You absolutely cannot get the private key from the public key or the address.
That one-way nature is key for security then.
Totally fundamental.
So, my private key, is it just like a password? Or is it something else?
It's literally just a number, a very, very large number.
How large?
A 256-bit number. I mean, you could theoretically generate one by flipping a fair coin 256 times and writing down the heads-tails sequence.
Really?
Yeah, but the absolutely critical part is how you generate it. It must come from a cryptographically secure source of randomness.
Okay.
You should never, ever try to write your own code to generate keys or just pick a number you think is random. It's incredibly easy to make a subtle mistake that completely compromises your security. Use standard, well-tested libraries and wallets.
Good advice. So how do wallets manage all these keys? Especially if every transaction creates a new change address, you could end up with hundreds of keys pretty quickly.
Yeah, that was a problem with early wallets. They were often non-deterministic or just a bunch of keys, GPO wallets.
Okay.
Yeah, they generated random, unrelated keys each time you needed one. Backing them up was a nightmare because you had to save every single private key individually.
Sounds messy.
Very. So modern wallets are usually deterministic wallets. They use a single starting point, a seed,
The seed.
a master key, essentially. From that one seed, the wallet can derive all the private keys, public keys, and addresses it ever needs in a predictable, deterministic way.
Ah, so you only need to back up that one seed.
Exactly. And the most advanced type are hierarchical deterministic, or HD wallets. They're defined by standards like BIP32 and BIP44.
Hierarchical.
Yeah, they generate keys in a tree structure. Parent keys can derive child keys.
What's the big advantage there?
The power isn't just about backing up the seed. It's that you can generate, say, public keys and addresses from a branch of the tree without needing the corresponding private keys.
Oh, interesting.
So imagine a business. They can generate a fresh public address for every customer payment using a public parent key on their web server without exposing the master private key, which might be kept offline.
That sounds much more secure for businesses.
It's invaluable for security and organization, yeah. You can track payments to specific addresses, manage different accounts, all derived from that single seed you backed up safely.
I've definitely heard about those backup phrases, like 12 or 24 words.
Yes. Those are mnemonic codes, or seed phrases, standardized by BIP39.
BIP39.
Right. It's a clever system that converts that random numerical wallet seed into a sequence of easily recognizable English words from a specific list.
Makes it easier to write down and store.
Much easier. And importantly, it makes wallets interoperable. You can usually restore your entire wallet, keys and all, in a different compatible wallet app just by entering those words.
Okay, that's handy. What about securing really large amounts of Bitcoin? Or situations where multiple people need control, like the charity example, Eugenia's charity, in the book.
For those scenarios, multi-signature, often called multi-sig or M of N addresses, are absolutely key.
M of N.
It means you need M signatures out of a possible N keys to authorize a transaction. For example, a 2 of 3 setup for a business partnership.
So like 2 partners out of 3 need to sign off.
Exactly. This ensures no single person can unilaterally control or compromise the funds. It provides a crucial layer of security and internal control.
Makes sense.
There are also other techniques like BIP38 for encrypting a private key with a passphrase, making it safer to store on paper or external media. And the book touches on survivability, thinking about estate planning, how funds can be accessed if the primary key holder is incapacitated or passes away. Multisig can help there too.
And quickly, what about those custom addresses, the ones that start with specific words, like maybe a charity using 1 kid?
Ah, those are vanity addresses.
Vanity addresses.
They're generated by essentially brute forcing random keys. You just keep generating keys and checking their addresses until you find one that starts with the desired pattern.
Is that less secure?
No, not inherently. The resulting key and address are just as secure as any other randomly generated one. It just requires a lot of computational effort to find one, especially for longer patterns. Sometimes people even outsource this to specialized vanity pools that have more computing power. It's mostly for branding or making an address more memorable.
Okay, so we have keys, addresses, wallets managing them. This all operates on that peer-to-peer network you mentioned earlier. What does that actually look like? How does it work on the ground?
Right, the network itself. It means there are no special nodes, no central servers, no single point of control or failure.
Everyone's equal.
Pretty much. All the computers participating in the network, the nodes, they contribute equally by validating transactions, validating blocks, and propagating that information to their peers. It's a true mesh network.
Like the early internet. Or BitTorrent.
Exactly like those examples. It's inherently resilient because there's no center to attack. If some nodes go offline, the network just routes around them.
It sounds like this ideal decentralized network where everyone plays the same role. But are all these nodes really doing the exact same thing? Or are there different functions within this peer-to-peer setup?
That's a great point. While all nodes participate in the peer-to-peer protocol, they don't all perform the exact same function or have the same capabilities.
Okay, so what are the types?
The most important distinction is between full nodes and lightweight nodes.
Full nodes.
Full nodes are really the backbone of the network's security and integrity. They download and store a complete copy of the entire blockchain history.
The whole thing. That must be huge.
It is. As of late 2016, the book mentions it was over 100 gigabytes, and it's grown substantially since then. It also requires significant bandwidth to keep up with new transactions and blocks.
I download everything.
Because by having the full history, a full node can autonomously and authoritatively verify every single transaction and block against all the network's consensus rules without trusting anyone else. They enforce the rules.
Okay, so they're the guardians of the rules. What about the lightweight nodes?
Those are often called SPV nodes for simplified payment verification, or just light clients.
And they don't download the whole blockchain?
No, they typically only download the block headers. These are much smaller, maybe 1,000 times smaller than the full blocks.
Block headers. What do they contain?
Metadata, essentially. The hash of the previous block, the timestamp, the mining difficulty target, and crucially, a summary hash, the Merkle root, of all the transactions included in that block.
So how do they verify payments if they don't have the full transaction data?
They rely on full nodes. They ask their peers, hey, is this transaction included in this block? And the full node can provide a small cryptographic proof, a Merkle proof, showing it's included under that header's Merkle root.
So they trust the full nodes for the details.
They trust the consensus represented by the chain of headers, and they trust the full nodes they connect to provide accurate Merkle proofs. It's much more convenient, uses less bandwidth and storage, but it does come with slightly weaker security and privacy guarantees compared to running your own full node.
Okay, so you have these different nodes. How do they initially find each other? This vast decentralized landscape, how does a new node join the party?
Good question. It's done through a process called network discovery.
Network discovery.
When a new node starts up for the first time, it needs to find at least one other active Bitcoin node to connect to. It might use hard-coded IP addresses of some well-known nodes or query special DNS servers called DNS seeds that return a list of active node IPs.
So it gets an entry point.
Exactly. Once it connects to one node, it performs a handshake by exchanging version messages, which contain information like the software version and the current block height.
A digital handshake.
Pretty much. They confirm compatibility with VERIC messages. After that handshake, the new node can ask its peer for the addresses of other nodes it knows about using GetAdd messages. The peer responds with a list using addr messages.
So it spiders out from the first connection.
Precisely. It builds up its own list of potential peers. The network is constantly adjusting, too. Nodes connect and disconnect, so they dynamically find new peers to maintain good connectivity.
And you mentioned earlier nodes keep track of unconfirmed transactions.
Yes, absolutely crucial. Nearly every node, especially full nodes, maintains a temporary storage area called the transaction pool, or more commonly, the mempool.
Mempool.
That's where valid transactions that haven't yet been included in a block reside. Miners typically select transactions from their mempool to build the next candidate block.
And there was another pool you mentioned.
The UTXO pool, or UTXO set. This isn't temporary like the mempool. Full nodes maintain this set, which consists of all the unspent transaction outputs currently available on the entire blockchain.
So all the spendable Bitcoin.
Effectively, yes. It's a snapshot of all the value that exists and can be spent. It's critical for quickly validating new transactions. Does this input actually exist, and is it unspent? Checking the UTXO set is much faster than searching the entire blockchain history every time.
Okay, so the network is constantly buzzing, nodes finding each other, sharing transactions in the mempool, validating against the UTXO set, and all this confirmed activity gets recorded onto the foundational ledger, the blockchain itself.
Yeah.
Let's dig into that structure.
Right, the blockchain. At its heart, it's surprisingly simple conceptually. It's an ordered, backlinked list of blocks.
Blocks of transactions.
Exactly. Each block contains two main parts. A header with all that important metadata we discussed, timestamp, previous block hash, mining difficulty, knots, Merkle root,
Right.
and then a list of transactions, often hundreds or even thousands of them, making up the bulk of the block's data size.
And the backlinked part.
That's the crucial chain element. Each block header contains the cryptographic hash of the previous block's header.
So block 100 points back to block 99.
Precisely. Block 99 points to 98 and so on, all the way back to the very beginning. This creates an unbroken, computationally secure chain. Tampering with an old block would change its hash.
Which would break the link from the next block.
Exactly, and invalidate all subsequent blocks. That's what gives the blockchain its immutability, growing stronger with every new block added.
And the very first block, the one that started it all, does it point back to anything?
That's the Genesis block, block 0. It's unique because it doesn't point back to a previous block. It's the hard-coded foundation of the entire chain.
The anchor.
The anchor, exactly. And interestingly, Satoshi embedded a hidden message in the Coinbase transaction of the Genesis block.
Oh, yeah? What was it?
It reads, "The Times 03 Jan 2009 Chancellor on brink of second bailout for banks."
Wow.
It serves as a timestamp, proving the block couldn't have been created before that date, and it's widely seen as a comment on the traditional financial system that Bitcoin was designed as an alternative to.
A little piece of history embedded right there. Now, speaking of the chain's integrity, we sometimes hear about blockchain forks. What are those?
Forks happen when the chain diverges. There are generally two types: hard forks and soft forks.
Okay, hard fork first.
A hard fork is a permanent split in the network. It happens when a change is made to the Bitcoin protocol's consensus rules that is not backward compatible.
Meaning older nodes don't accept the new rules.
Right. So nodes running the new rules start building a chain that nodes running the old rules see as invalid, and vice versa. This leads to two separate, independent blockchains, and usually two separate currencies. Think Bitcoin and Bitcoin Cash, for example.
A permanent divergence. What about a soft fork?
A soft fork is different. It's a change to the consensus rules that is backward compatible, usually by making the rules stricter.
Stricter. How does that work?
Imagine a new rule says blocks must now be smaller than before. Older, unupgraded nodes will still see blocks created under the new stricter rule as valid because they already fit the old, looser size limit.
Ah, I see.
But blocks created under the old, looser rules might be rejected by the newer, upgraded nodes, enforcing the stricter rule. So eventually, the entire network converges on the new, stricter rule set without necessarily splitting the chain. It's generally seen as a safer way to upgrade the network. SegWit was implemented as a soft fork.
Okay, that makes sense. And for developers who are actually building applications on Bitcoin, they need ways to test their code safely, right? They can't just experiment on the live network with real money.
Absolutely not. That would be reckless.
Ah.
Thankfully, Bitcoin Core, the main software implementation, provides dedicated test blockchains for exactly this purpose.
Test blockchains.
Yes, the main one is called testnet. It's a public test network that runs parallel to the main Bitcoin network, mainnet. It has its own testnet coins, which are intentionally worthless, that developers can get easily from faucets.
So they can experiment freely.
Exactly. Testnet tries to mimic the behavior and conditions of the real network, unpredictable block times, transaction fees, etc., but without any real financial risk.
Is that the only option?
There's also regtest, which stands for regression testing mode. This creates a local, private blockchain on the developer's own machine.
Private.
Yeah, you control everything. You can generate blocks instantly, create transactions without fees, set up specific scenarios. It's perfect for rapid prototyping and automated testing in a controlled environment.
So there's a pipeline for development.
A very important one. You typically develop and run initial tests locally on regtest for speed and control. Then you move to testnet for more realistic dynamic testing involving interactions with other testnet users or services. And only when you're completely confident after thorough testing on both would you deploy your application to mainnet to handle real Bitcoin.
Test, test, test. Seems crucial. Okay, so we've covered transactions, keys, the network, the blockchain.
Okay.
But we keep mentioning miners. Let's finally dive into mining. What exactly is it, and how does it secure this whole system?
Right. Mining. It's the process that serves multiple crucial functions simultaneously. It's how new Bitcoin is created and introduced into the system.
Through that Coinbase transaction.
Exactly. It's also how transactions are gathered, validated, and confirmed by being included in the blockchain. And critically, it's the mechanism that secures the entire network through that proof of work concept.
And it's competitive.
Incredibly competitive. It's a massive global industry now, with specialized companies running data centers full of dedicated hardware. These miners are essentially competing in a constant hashing race.
A hashing race. You mentioned that earlier.
Yeah.
What are they racing to do?
They're trying to find a solution to a specific mathematical puzzle related to the block they want to add to the chain. Specifically, they're trying to find a hash value for their candidate block header that is less than a certain target value set by the network.
A target value.
Think of it as trying to roll a pair of dice and get a result lower than, say, 3. But in Bitcoin's case, the target is an incredibly small number.
It's hard to find.
Astronomically hard. Miners basically take their candidate block header, which includes the Merkle root of the transactions, the previous block's hash, etc., add a random number called a nonce, and compute the hash of the whole thing using the SHA-256 algorithm twice.
Okay.
If that resulting hash is below the current target, great. They've found a valid block, they win the reward, and they broadcast it.
And if it's not below the target?
They change the nonce slightly, just increment it by 1, usually, and hash again. And again, quadrillions of times per second across the entire network. It's essentially a brute force lottery.
Quadrillions of tries. Wow. That sounds incredibly energy intensive.
It is. That expenditure of energy, the work in proof of work, is what underpins the security. It makes it prohibitively expensive for anyone to rewrite blockchain history because they'd have to redo all that work.
Okay, so the hashing race is the work. How does the economic model, the rewards, the halving, actually reinforce the security? Does it keep miners honest?
The economics are absolutely central. Bitcoin has that fixed, predictable, and diminishing money supply we talked about.
Right, the halvings.
Exactly. The block reward, the amount of new Bitcoin created in the Coinbase transaction, started at 50 BTC back in 2009. It halved to 25 BTC around 2012, then to 12.5 BTC in 2016, 6.25 BTC in 2020, and most recently, in 2024, down to 3.125 BTC per block.
Halving roughly every 4 years.
Precisely, every 210,000 blocks. This continues until around the year 2140, when almost all of the maximum 21 million Bitcoin will have been issued. After that, miners will be rewarded solely by transaction fees.
So this limited supply is by design.
Absolutely. It's designed to be deflationary, or at least disinflationary, over time. This predictable, constrained supply is a core feature, standing in stark contrast to traditional fiat currencies where central banks can effectively print more money at will.
Which can lead to inflation, a kind of hidden tax.
Exactly. Bitcoin scarcity is programmed in, transparent, and based on mathematical rules, not political decisions. This predictable issuance is a key part of the incentive structure for miners to invest in hardware and energy to secure the network.
Now, how does the network keep those block times hovering around 10 minutes? With all this new hardware coming online, surely blocks would get found faster and faster.
That's where another ingenious mechanism comes in. The difficulty adjustment.
Difficulty adjustment.
The network automatically recalculates the difficulty target that number miners are trying to hash below every 2016 blocks.
Which is roughly?
Roughly every 2 weeks, if blocks are averaging 10 minutes. The network looks back at how long the previous 2016 blocks actually took to find.
Okay.
If they were found faster than 10 minutes on average, meaning total hashing power increased, the difficulty target is lowered, making the puzzle harder, for the next 2016 blocks.
To slow things back down to 10 minutes?
Exactly. And conversely, if blocks took longer than 10 minutes on average, meaning hashing power decreased, the target is raised, making the puzzle easier.
So it self-regulates.
Perfectly self-regulating to maintain that 10-minute average block interval, regardless of how much total hashing power is competing on the network. It's remarkable.
So a miner finds a valid block below the target. What happens next? How does the network agree this is the correct next block?
Once a miner finds that winning hash, they immediately broadcast the completed block to all their connected peers.
Spreading the news.
Yep. Each node that receives it independently validates the block. Does the header hash meet the difficulty target? Does it correctly reference the previous block? Are all the transactions inside valid? Correct signatures, inputs unspent, etc. Does the Coinbase transaction create the right amount of new Bitcoin?
Checking all the rules.
Every single rule. If the block is valid according to that node's rule set, the node adds it to its own copy of the blockchain.
Okay.
And crucially, it immediately starts trying to mine the next block using the hash of the block it just received as the previous block hash for its new candidate block.
So building on top of it.
Exactly. That act of building on top of a received block is essentially how nodes vote with their mining power. They are endorsing that block as the legitimate extension of the chain. The longest valid chain, the one with the most accumulated proof of work, is considered the authoritative version of history by the entire network. That's Nakamoto consensus.
Built on proof, not trust. Okay, this sounds incredibly robust, but I have heard about potential vulnerabilities, specifically 51% attacks. Is the system truly infallible? What are the limits here?
That's the right question to ask. No system is truly infallible, and Bitcoin's security model has theoretical limits. The most discussed is the 51% attack.
Okay, what is it?
It's a scenario where a single entity or a coordinated group of miners manages to control a majority, meaning more than 50% of the entire network's total hashing power.
Over half the computing power. What could they do with that?
With that much power, they could potentially disrupt the consensus process going forward. For instance, they could mine blocks faster than the rest of the network combined.
Right.
This would allow them to deliberately create a fork or chain split. They could mine their own secret chain, perhaps containing different transactions than the public chain the rest of the network sees.
A secret chain. Why?
The primary goal is usually to double spend their own funds. Imagine they pay a merchant on the public chain, chain A. That transaction gets confirmed. Then they release their secret, longer chain, chain B, where that payment never happened.
Uh-oh.
Since nodes follow the longest valid chain, the one with the most work, the network might switch to chain B, effectively erasing the original payment from history. The attacker gets their money back, even though the merchant thought they were paid.
So they reverse their own transactions.
Yes. They can also potentially execute denial of service attacks by refusing to include specific transactions or blocks from other miners in their dominant chain.
Okay, that sounds bad. But could they steal my Bitcoin if I wasn't involved in their transaction? Could they change old blocks?
No. And this is a really critical misconception that needs clearing up. A 51% attack cannot steal Bitcoin from addresses they don't control. They still need valid private key signatures, spend Bitcoin without valid signatures, redirect funds belonging to others, or change past transaction records that are already deeply buried in the blockchain.
So my old transactions are safe.
The further back a transaction is, the more computationally infeasible it becomes to reverse, even with 51% power. Bitcoin's ledger becomes exponentially more immutable with time and block depth. These attacks primarily affect future consensus or, at best, only the most recent blocks that haven't received many confirmations yet.
So it's about disrupting the present or very recent past, not rewriting deep history or stealing existing funds.
Exactly. It's about undermining confidence in future transactions or censoring specific activity or reversing your own recent spending. And the 51% figure isn't even absolute. Attacks can be attempted with less power, but the probability of success drops dramatically, and the economic costs and risks usually outweigh any potential benefit. It's generally considered economically irrational for a majority miner.
Okay, that's a crucial clarification. So moving beyond just currency, the book emphasizes that the blockchain offers these fundamental building blocks for much broader applications. What are some of those core guarantees it provides?
Right. The blockchain isn't just a ledger. It's a platform providing some incredibly powerful and, frankly, novel guarantees. We've touched on some already.
Like no double spending.
That's fundamental, yes. Then there's immutability, which, as we discussed, is underwritten by the sheer energy cost of proof of work and grows stronger over time. The system provides neutrality. Valid transactions get processed regardless of who sends or receives them. There are no gatekeepers in that sense. You get secure timestamping because blocks are ordered and linked cryptographically.
What else?
Authorization is guaranteed via those digital signatures. Only the key holder can move funds. Auditability is inherent because the ledger is public. Accounting is strict. Inputs must equal outputs plus fees, so value isn't created or destroyed within transactions, except the Coinbase.
That's a lot of guarantees.
There's more. Non-expiration valid transactions generally don't expire just sitting in the mempool. Integrity-signed transactions can't be modified by anyone else. Transaction atomicity, transactions are all or nothing. They either fully succeed or completely fail, no partial states. And finally, replication through thousands of nodes ensures data durability and consistency, ensures everyone eventually agrees on the same history.
Wow. Okay, those are some powerful building blocks. How do developers actually use these to create new things on top of Bitcoin?
Well, one fascinating early application explored in the book is colored coins.
Colored coins.
Yeah, it's a clever idea. It uses a small specific data field in a transaction output called OPRETURN. You can embed a tiny bit of metadata in there.
Metadata like what?
Metadata that gives special meaning to the specific Bitcoin units, UTXOs, being transferred in that transaction. So you could color some Satoshis to represent, say, a share certificate in a company.
So the Bitcoin itself represents something else.
Exactly. Or it could represent a deed of ownership for a physical asset, a concert ticket, a digital collectible. The Bitcoin transaction secures the transfer of this colored asset, leveraging all those blockchain guarantees like immutability and auditability. It's about layering new meaning onto Bitcoin's base layer.
Interesting way to leverage the existing security. And perhaps the biggest advanced application, the one designed to help Bitcoin scale for like everyday payments, is the Lightning Network.
The Lightning Network is indeed a monumental development. It's a second-layer routing technology built on top of the Bitcoin blockchain.
Second layer, meaning not directly on the main chain.
Right. It uses Bitcoin's base layer features like multi-signature capabilities and time locks to create off-chain payment channels.
Why off-chain? What problem does it solve?
It tackles the fundamental challenge of scaling Bitcoin for frequent small payments. Every transaction on the main blockchain incurs a fee and takes time, at least 10 minutes for one confirmation, potentially longer for high security. That's just not practical for buying coffee or streaming video second by second.
Fees and delays add up.
Exactly. The Lightning Network aims to make Bitcoin payments almost instant, incredibly cheap, and handle a vastly higher volume of transactions.
How does it make payments almost instant and nearly free if they're not on the main chain?
Okay, let's use the book's example. Emma wants to stream video from Fabian, maybe paying per second.
Right, micropayments.
Yep.
Impossible on chain.
Totally. So, instead of a blockchain transaction every second, Emma and Fabian open a single payment channel between them. This involves creating one initial transaction on the main Bitcoin blockchain, a funding transaction that locks up some Bitcoin from both parties into a shared 2 of 2 multi-signature address.
Okay, funds are locked on chain to start.
Yes. Now, off-chain, they can exchange updated commitment transactions between themselves as often as they like, instantly and with virtually no fee.
Commitment transactions.
These are valid signed Bitcoin transactions that represent the current balance split within the channel. So after 1 second of video, they exchange transactions showing Fabian has slightly more of the locked funds and Emma slightly less. After 2 seconds, another update, and so on.
But these aren't broadcast to the network.
No, they just hold on to the latest signed commitment transaction from the other party. Only when they want to close the channel do they broadcast the final state, the last commitment transaction to the main blockchain as a settlement transaction.
So only 2 on-chain transactions needed. One to open, one to close, regardless of how many payments happened off-chain.
Precisely. And these commitment transactions are very cleverly designed using things like time locks and revocation keys to ensure neither party can cheat by broadcasting an old state where they had more money. If someone tries to cheat, the other party can detect it and claim all the funds in the channel as a penalty. It maintains trustlessness.
Oh, wow, that's clever. What about paying someone you don't have a direct channel with?
That's where the network part comes in. Lightning supports multi-hop payments. If Alice wants to pay Eric, but only has a channel with Bob, and Bob has one with Carol, and Carol with Eric.
A chain of channels.
Exactly. Alice can route the payment through Bob and Carol to reach Eric. And the technology used for this is really neat. It's based on onion routing, similar to what Tor uses for privacy.
Onion routing.
Yeah. Alice constructs the payment instructions in layers, like an onion. Each intermediary node, Bob, Carol, can only peel back their layer, seeing who the payment came from immediately before them and where to send it immediately next.
So Bob only knows Alice and Carol.
Right. Bob doesn't know Eric is the final recipient, and Carol doesn't know Alice was the original sender. It preserves the privacy of the full payment route.
Even the path length is hidden.
Yes, the routing information is typically padded to a fixed length, say 20 hops, so intermediaries can't even easily guess their position in the route based on the data size. It's all designed for privacy and efficiency.
So Lightning significantly boosts Bitcoin's capabilities, right? Without changing the base layer.
Absolutely. It layers on top, leveraging Bitcoin's core security features to provide massive increases in transaction capacity, speed, privacy, and granularity, allowing for tiny micropayments. And it does all this while upholding that core principle of trustless operation without needing central intermediaries. It's a huge step towards making Bitcoin practical for widespread everyday use.
Okay, shifting gears slightly, but related to security. The source, Mastering Bitcoin, makes a really strong point about Bitcoin's security model being fundamentally different from traditional systems. What's that difference?
Yeah, this is a key insight for anyone building on Bitcoin. Traditional security, like in corporate IT or banking, is usually built around a root of trust.
A central point.
A central, most trusted core component may be a specific server or authority. Security layers are then built outwards from that core. The problem is, the more complex the system gets, the more potential vulnerabilities are introduced, often relying implicitly on the security of many different components.
Okay. How does Bitcoin differ?
Bitcoin completely flips this model. Its root of trust isn't a single server or company, it is the decentralized consensus system itself, specifically the fully validated blockchain reflecting the most proof of work.
The blockchain is the root of trust.
Exactly. The crucial takeaway for developers is you should never place explicit or even implicit trust in anything but the blockchain itself when designing secure Bitcoin applications. Don't trust your own server completely. Don't trust a third-party API completely. Don't even trust the node software itself implicitly. Always verify against the blockchain consensus.
So if one component in your Bitcoin application is compromised, say your web server gets hacked, the whole thing shouldn't fall apart.
Ideally, no. A robust security design involves thinking. What happens if this specific component is completely compromised? Is my application still secure? Can funds still be protected?
And if the answer is no,
It means you've misplaced trust. You've relied on that component security instead of relying solely on the guarantees provided by the underlying blockchain and cryptographic principles. The blockchain should always be your ultimate arbiter of truth and security.
that's a different way of thinking about security design. How does something like segregated witness or SegWit fit into this security picture? You mentioned it earlier.
SegWit, which was activated on the network via a soft fork around Bitcoin Core version 0.120.13, addressed several key issues, including a major one called transaction malleability.
Malleability. Sounds bad.
It was problematic. Before SegWit, a third party, like a node or miner relaying a transaction, could sometimes slightly change the transaction's unique ID, its TXID, after it was signed and broadcast, but before it was confirmed in a block.
Could they change where the money went?
No, crucially, they couldn't change the sender, receiver, or amounts. But changing the TXID, even subtly, could break chains of dependent transactions. If you built a second transaction that spent the output of the first one using its expected TXID, that second transaction would become invalid if the first one's TXID was malleated before confirmation.
So it messed up multi-step processes.
Exactly. It made complex smart contracts and layer 2 solutions like the Lightning Network much harder or even impossible to implement reliably. SegWit fixed this by separating the part of the transaction that could be malleated the signature or witness data from the part used to calculate the TXID.
Segregated the witness. Hence the name.
Precisely. The TXID is now calculated without the witness data, making it immutable once the transaction is created.
Did SegWit bring other security benefits?
Yes, a significant one, especially for hardware wallets or other offline signing devices. Before SegWit, when signing a transaction, the signer often needed access to the full previous transaction data to know exactly how much value was in the input being spent to prevent being tricked.
That sounds cumbersome for offline devices.
It was. They potentially needed to stream large amounts of data. With SegWit transactions, the value of the input being spent is now explicitly included as part of the data that gets signed.
So the signer knows the amount directly.
Yes. The hardware wallet can now trust the input value stated in the transaction data itself, because if that value is incorrect, if someone tries to trick it into signing away more value than expected, the resulting signature will simply be invalid when verified against the actual UTXO on the blockchain. It dramatically simplifies secure offline signing.
And economically.
It also cleverly realigned economic incentives. Data stored in the witness part of the transaction gets a 75% discount on transaction fees compared to data in the main transaction block.
Why the discount?
This encourages the use of SegWit transactions and, more broadly, transaction types that help reduce the overall size of the UTXO set, that critical database all full nodes have to maintain. Reducing UTXO bloat is good for the long-term health and scalability of the network, so it incentivizes efficiency.
Wow. What a journey through the layers of Bitcoin. It really is so much more than just, nerd money.
Absolutely. From that simple idea of peer-to-peer digital cash
Yeah.
to this incredibly complex, resilient, decentralized network built entirely on cryptographic proof, not on trusting any single entity.
Right, and we've seen how every single component, the keys, the UTXO model for transactions, the
Mm.
peer-to-peer network, the blockchain structure, the mining and consensus rules, play such a vital interconnected role in the system's overall integrity and function. It really does feel like a system designed with incredible foresight, leveraging principles, as you said, found even in nature to create something robust and adaptable.
It is, and it's clearly more than just a payment system, isn't it? It's emerged as this foundational layer, a platform for entirely new kinds of trust services, many of which we're probably only just beginning to imagine or explore.
So listening to all this, thinking about these intricate mechanics, the robust building blocks of a decentralized system like Bitcoin, it makes you wonder, how might you, listening now, imagine these core principles, decentralization, cryptographic proof, transparency, immutability being applied, maybe to solve problems in your own field or in areas completely outside traditional finance? What new possibilities does this deep dive spark for you?